is an expert in classical algorithms. She's done a lot of work there, but about a decade ago, she was one of the early movers who decided that simulation and chemistry were interesting questions, and so she just jumped into it and started working on it at UC Irvine and proved some really fundamental results. The computation complexity of the local Hamiltonian problem.
So I think the format of this morning's talks differs slightly than the sort of what Umesh described as the high level and deep dive. The yin and the yang, I think, of this morning's talk are sort of good news, bad news. I told us this morning about all the wonderful things that we expect that quantum computers to be able to do, and I'll talk more about hardness results and some of the limitations, at least in the theoretical sense. Okay, so we're talking about the local Hamiltonian problem. Let me start with the definition. Okay, so we have a system of n qubits, qubits, some finite dimensional particles, and a Hamiltonian term that describes the physics of the interaction of these particles. Okay, and this is presented to us in this nice compact form. We have R terms, each of which operates on a small constant number of the particles. We'll call this number k, and the dimension of our individual particles is d. And it's not too hard to arrange things so that we have a bounded norm of 1 to each of these terms. And so along with this is the problem definition. We get two numbers, an energy and a delta. And the delta is usually 1 over polynomial in n. And the question that we want to answer, essentially what we're asking is, what's the ground energy of this system? So is the smallest eigenvalue of the matrix that I get, if I add all these terms together, is it less than E, or is it at least E plus delta? So we give ourselves a little margin of error here with this delta, and we want to know if it's below one or above the other. And it's a promise problem in that if it's in the region between, we don't have to answer correctly. Okay. So this problem has appeal to a lot of different groups. This is a fundamental problem in condensed matter physics. A lot of numerics of condensed matters is solving exactly this problem with various different types of Hamiltonian terms, different geometries of the qubits. So this has been a fundamental problem in physics, but also appeals to computer scientists because it's essentially a quantum version of constraint satisfaction. So if it happens that these individual terms are all diagonal in what we call the standard basis, or the basis defined by these qubits, then this is essentially constraint satisfaction, okay, which is a generalization of Boolean satisfiability. So it's a fundamental problem for us as computer scientists, as well as an important problem for physicists. And as I pointed out, this is something that we want to be able to solve on near-term computers as a starting point of quantum simulations as well. So a lot of different reasons why we care about this. So if it's going to be a generalization of SAT, then I need a generalization of NP to describe the complexity or the computational complexity of solving this problem. So the
Eigenvalue SAT?
What?
Why is the eigenvalue so complicated?
Essentially, if all of these matrices are diagonal, it's defining a function. If I set these variables to this value, that's going to be the function. Each of these is a little function on k different variables, telling you the cost of setting those variables to a particular value. And so what I'm looking for is some global setting of all the variables such that the sum of the costs is as small as possible. So that's essentially, and you can think of this even, let's talk about as a Boolean satisfiability problem. Let's see these are 1, 0 variables. Each of these could be thought of as a clause that says if I set the Boolean variables in a certain way, it's satisfied or it's not satisfied. And I'm asking for a global setting of all the variables.
The sum is over the Boolean cube and not over R?
Yeah, so now, so the basis for the space is the Boolean cube. In general, when these are general matrices, the ground state could be a superposition. But that doesn't happen in the special case where these individual matrices are diagonal. If they're all diagonal, then the optimal solution is also going to be on that diagonal. So it'll be a classical state instead of a quantum state.
Is what's bothering you the fact that it's an exponential dimensional matrix?
Oh, it's exponential size. That's the thing.
Yes, yeah. Sorry, okay, thank you. Yeah, so the description of my problem is polynomial, but when I put this together, if I were to write this out, this would be a 2 to the n by 2 to the n matrix, okay? All right, thank you. Okay, so NP, the problem definition here is that I have an instance, which I'll call X, and we have a verifier. If X is in the language, there's some type of witness that my polynomial time verifier can verify that it's in the language. And if it's not in the language, no matter what witness you give me, the verifier is going to reject, okay? And we know that Boolean satisfiability is NP complete. So the quantum version of NP is QMA, okay? So now we're defining our verifier as a circuit family, a quantum circuit family. And if X is in the language, then now the witnesses are quantum. There's some type of quantum witness that will cause my circuit to accept with reasonably high probability, 2/3 in this case. And if X isn't in the language, no matter what witness you're given, the probability of acceptance is at most 1/3. And we'll talk about this, but the punchline is that local Hamiltonian is QMA complete. So it's complete for this class. And these probabilities can be boosted so that they're arbitrarily close to 1 and 0. Okay. So for containment, for Boolean satisfiability to show that it's an NP, the witness is just the assignment to the variables, and you can then check that it in fact satisfies your assignment. So similarly, in the QMA world, we're asking, is there a state that causes the energy to be less than a certain amount? And the witness is that state, okay? So I'm not going to talk too much about containment, but we need some type of way of given a state to measure it. So we're guaranteed that the energy is at most bounded by E, or at least E plus delta. And we need a way to measure the average energy of this state. So there's a circuit that can do that. And if you repeat this enough times, you can distinguish between these two cases. So it's not too hard to show the containment. The more tricky part is showing the hardness. Okay, so a proof that local Hamiltonian is QMA hard starts with some generic language in QMA, okay? What does it mean to be in QMA? It means I have this quantum verifier that can do this verification. So here's what the quantum verifier would look like. X is hard-coded as the input, and I have some potential witness here. And this circuit will accept or reject if there's a witness that causes it to accept or reject. So this is sort of the basic qualification for being in QMA. And now we want to translate that or reduce that to an instance of local Hamiltonian. Okay? So on the left-hand side, I have the circuit that says if X is in the language, there's some witness that causes it to accept. If X is not in the language, no matter what I plug in here, the probability of acceptance is low. And I'm translating that into a Hamiltonian problem. A Hamiltonian problem consists of these three components: the Hamiltonian itself, the bound, and the distance. And so I have to translate it into a Hamiltonian whose ground state is less than E if X is in the language, if there is a witness that causes this circuit to accept, and the ground energy is at least a certain amount if there's no witness that causes it to accept. Okay? And X definitely needs to be hard-coded into this Hamiltonian here. Okay? Okay, and so Kitaev's original construction showed that the 5 local Hamiltonian is QMA complete. I'm not going to go through the whole construction, but I'll give you a snapshot of what the ground state looks like, or what the actual construction looks like. So the ground state of the Hamiltonian that's constructed shows the entire history of the verification process. So we have 2 registers here. Here's a clock register, And here's the actual computation register that's simulating the computation of the circuit. Okay, so it's a superposition of all the different points of time in this circuit, from 0 all the way to t, and I'm assuming that my circuit has t gates. Okay, and it's a supervision of what the circuit looks like at the beginning, what it looks like after 1 gate's applied, after 2 gates applied, all the way up through t. And the fact that I'm entangling each of these computation states, these snapshots of the circuit, with a clock register means that they're not going to, there's going to be no negative interference. So it really is sort of an equal superposition of the entire history of this computation. Okay, and then we need that the spectral gap is at least a certain amount because we want, in the case that it's not accepting, that there's going to be a high energy. There are 2 additional components to the Hamiltonian. One locks in the input that just basically says at time 0, the X register needs to have the correct input, whatever I want it to be. So this induces an energy penalty if the jth bit is wrong. If at time 0, the contents of this register should just have the input to my circuit. And so this says if we're at time 0 and the input is wrong, there's going to be a penalty. Yes?
Why do you need the spectral gap and not the promise gap?
Because in the event that it's non-accepting, and there's going to be some penalty for non-accepting, I want to make sure that I'm not cheating by my circuit not being in this ground state. So there's a penalty for not being in this ground state, so that the state itself really does have to represent the accurate construction of the circuit.
Maybe it's a terminology.
But this really is the spectral gap of this particular Hamiltonian, and I need it to be at least a certain amount, so you can imagine I want to cheat, okay? I want to somehow make this ground state look like an accepting state by not actually having my state represent the computation. There's a penalty for that.
And if it's the case that you send another witness that has not the maximum acceptance probability, but slightly perturbed, then you wouldn't have, it would still be a history state, but not from the same witness, right? So it still has the same form that you're saying. Do you understand what I mean?
No, I didn't understand that.
Imagine that you have another witness that's orthogonal to the first one.
Right.
But it has slightly less, the accepted probability is slightly smaller.
Okay. But good enough?
But good enough.
Okay, that would work too.
Yeah, but the spectral gap could be smaller, right?
No. So for any correct computation, no matter, this is just saying for, as long as I'm inputting 2 things to my circuit, X and the witness, okay? And this will have, this will be in the ground state if I'm a correct computation for that witness, whatever it happens to be, whether it's accepting or not. And there's going to be a penalty if my state doesn't represent the correct execution of that circuit. Okay? Okay, and the final term says we have to accept. At time t, at the end of the circuit, if whatever my output bit of my circuit is, if it's not accepting, that's going to introduce an energy penalty. Okay? And we put these together, and that's the whole Hamiltonian construction. All right. This is like a very quick introduction to the Kitaev construction. So I can imagine different variations of this problem. Okay? And I'm going to focus mostly on the sort of the different varieties of things that people have studied. Locality tells me for each of these terms how many different particles each term can operate on. Locality is a little bit of a deceptive term because we associate it with spatial locality. It's really not. It's really just a mathematical concept that says each one of these terms operates on some number of particles. It doesn't actually refer to some embedding in real space and locality. Okay? So I can play with the dimension of my individual particles. And I can also look at a more physically realistic situation in which these particles are in fact embedded in some space. We often look at a 2D grid where the particles sit on the vertices of the grid and we allow interaction terms along the edges. So this picture is a two-local Hamiltonian because I have interaction terms along each edge that I'm adding together. Okay, so these are the different varieties that you can imagine studying. So just to step through some of the progress that has been made on this problem, Kataev originally showed that 5 local 2-state qubits is QMA complete. That was the original proof. Later, this was shown to actually work on a 2-dimensional space. So in 2 dimensions, 2 local, and each of these individual particles has 6 dimensions to it. Later improved to 2 local 2-state, and then even on the grid. So even if I have qubits here, it's 2 local. It's still QMA complete. And then we came along and actually proved that this can be extended to the 1D line. So the one-dimensional analog of this. I'm going to say a little bit about this paper first, and the relationship between QMA and adiabatic computation, because they're sort of intimately connected. So I gave us a nice intro and set us up pretty well for adiabatic computation. We're studying in the ground state of some Hamiltonian that's supposedly easy to prepare. We are coming up with some Hamiltonian whose final ground state encodes the answer to some computational problem that we're interested in. And then we slowly evolve. I've drawn it as a straight line here, but you could imagine there's potentially a curved line through Hamiltonian space. But this is sort of the most natural version of just slowly taking a convex combination of the 2 Hamiltonian terms. Okay, so, and as I mentioned, that the speed with which we can travel from one to the other depends on the spectral gap of the Hamiltonians as we go. So we're bounded, we can't go faster than the inverse of the spectral gap as we progress from one Hamiltonian to the other. And the final measurement, then we do some final measurement to get the answer to our problem. So we evolve slowly to this term. If we go slowly enough, we stay in the ground state. So hopefully at the end of this process, we're sitting in the ground state and we can measure and get an answer to our problem. So originally this was suggested as a way of potentially using quantum computers to solve NP-hard problems. And possibly adiabatic computation can be more robust against certain types of errors. And the question is, how does this relate to our traditional circuit model? What's the relationship between the two? Can a quantum circuit simulate an adiabatic computation? The answer is yes. More interesting for us is, can an adiabatic computation perform anything that a circuit can do? And here the answer is also yes. And it's often intimately connected with these QMA hardness results, because the constructed Hamiltonian looks a lot like the propagation history state that we use for the hardness results. So in this case, the final Hamiltonian that we construct is going to be equal to the propagation Hamiltonian of the circuit that we want to simulate. So we're asking, through adiabatic computation, can I simulate a circuit and get the same answer? And so the final Hamiltonian that we pick is exactly this, the Hamiltonian whose ground state is this history state, minus the witness. We're just asking for a particular input. Does my circuit accept or not? So this is what the start state would look like, all zeros, easy to prepare. The final Hamiltonian is the propagation Hamiltonian for this circuit. Hopefully at the end, we end up with this history state for this circuit. And to measure, we ask, okay, we measure the clock state. And if I'm in the last clock state, then we measure and say, is the output 1? So we only get the correct answer when we measure the clock state if we happen to be in the last time period. And this succeeds with probably 1 over t plus 1. So there's some probability error, but you can repeat this polynomial number of times and get the answer to your circuit. So a lot of times these QMA completeness results sort of go hand in hand with a comparable adiabatic result. And so when it was proven that the 2-dimensional local Hamiltonian problem is QMA complete, it also had the effect of proving that you can actually simulate this adiabatic computation of a circuit in 2 dimensions as well. Okay, so, and we've encoded the input into the state of the circuit. So there's a little bit of extra work to show that not just the start state and the final state have a large spectral gap, but everything in between. Okay, so this is, by the way, the actual sort of the matrix for the propagation. Okay. I also want to say a little bit about how we actually achieve these sort of, how we can actually get this 2-dimensional result. The original Kitaev construction had a computation register and a clock register that were conceptually quite separate. Okay, so we don't think of these as existing in space. And then to advance the clock requires an operation on the clock qubits as well as the computation bits. So I'm saying if I advance the clock, then I have to apply a gate. Okay. So in order to, this is very non-spatial because I'm grabbing some qubits from the clock and some qubits from the computation. And so in order to actually sort of execute this in some spatial dimension, I need to actually have the clock somehow distributed through this 2-dimensional grid. And so each particle now encodes a qubit as well as some encoding of a clock. And I'm using colors to denote this. Okay, so the idea is that you have this pattern of colors, and that tells you a clock state. So I think of sort of the computation going from left to right as I'm executing, you know, the teeth gate. These are, we've executed 3 steps of the gate. We have several left to go, and each column tells you the state of the circuit at a particular point in time. And as we progress from left to right, the particles go from yellow to black. It progresses from left to right, and the clock advances. So this is the active column that actually is encoding qubits, and the Hamiltonian propagation is acting upon 2 terms. So the essential idea is that we're using some local Hamiltonian terms to say certain patterns of colors are forbidden, and we're using certain propagation terms to say, okay, I'm applying a gate and I'm advancing the clock in some way. So the clock is somehow represented in this pattern of colors in this grid. And the actual mechanics of this are I won't go into, but basically you can think of a clock state now as a pattern of colors. Okay? And if I look at sort of the set of clock states, I have a bunch of invalid clock states, which I've invalidated by some penalty term. And these are the actual clock states that represent the same kind of progress through time as the Kitaev clock, which was numbered 0, 1, 2, 3. Okay? So we're actually just taking that clock and distributing it through the 2D grid. The one-dimensional construction is very similar. But let me just say a little bit about why the 1D result was a little bit surprising in this context. First of all, numerically, physicists have had a great deal of success finding ground states heuristically in 1 dimensions, whereas 2D seems to be quite difficult in terms of the actual classical simulation and finding ground states. So in particular, the density matrix renormalization group method developed by Steve White at UCI was one of the most successful methods at actually using classical computers to find ground states, and was largely very successful. And then also, if you look at the classical analog, the version of constraint satisfaction where the variables are on a line, this is actually solvable in P. So the classical analog in this case is in P, whereas in 2D it's NP complete. But the difference here is that we can use quantum superposition as an extra dimension to encode the progress of the circuit. Okay, so it's kind of a similar construction where we have this patterns of colors and we're moving the circuit through time. And we're shifting, we sort of execute one gate and then shift the qubits over. and then there's some sort of cursor qubit that's sort of traveling around, carrying information back and forth. So there's this active site that triggers the execution of a gate and then moves qubits around the system. So it's a similar type of construction that accomplishes this in 1D. I think I will skip over this part.
Question?
Yes?
So you'll still need to have the number of qubits being proportional to the depth of the circuit, right?
Right. So the number of Q particles is still n, the number of qubits in my circuit I'm simulating, times t, the size. I've just taken that grid and flattened it out.
So that means, if I understand still, that there are polynomial gaps in other resource constraints, like in size and maybe in still in some time variables, because there may still be, for example, a square root speed up in one model versus the other one.
Yeah, so you're saying that there may be a more efficient construction that doesn't have this product of the qubits times time, yes. And I think in most of these sort of spatially distributed ones, it needs that product, so you have to record it that way. So, but not so in the Kitaev construction where you just have the two. So, yeah.
So is there something you can say about when you talk about these states, you talk about copying and moving stuff around, because of course what you have is a Hamiltonian and it's
right.
ground state. So can you do the translation between, why is it okay to think about dynamics behind it, even though it's a static problem?
Right, and okay, so the question, I suppose I should repeat the question for, so the question is, I'm talking about this dynamic situation where I've got this particle that's moving information around and this process that's happening. And that's the beauty, I think, of the Kitaev construction, is that you can take a process, a computational process, and encode it in a static circuit. So much like the way we take the process of a Turing machine and encode it in a static Boolean satisfiability problem. So, we can think of the circuit as changing information through time, which is what we do, and we represent all of that in some static Boolean satisfiability problem. Similar here, I'm thinking of this as some process by which there's this little cursor moving around and moving information and such. But at the end of the day, all of that is encoded into this propagation Hamiltonian that enforces that the ground state is the whole movie of that process. Each frame is encoded in the ground state. So underlying all of this, we start sort of naturally talking about encoding processes into the ground state. It's always that translation of of using the propagation Hamiltonian to translate that into the ground state. Does that help?
Yeah, but I was hoping you would do it at a slightly more granular level. Yeah.
Okay, so I think I actually had, maybe I'll go back to this slide. Here. So I want this to move forward, okay? So I want this cursor to somehow go from here to here, and I want to encode that in my Hamiltonian. This is the term that doesn't, okay? It says that basically it enforces the fact that before the step is executed, the amplitude of that state has to be equal to the amplitude of the state after the step is executed. And that's what this Hamiltonian term says. It says at time t, if you're in this state, that at time t plus 1, you better be in this state. And if you're not, there's going to be an energy penalty to pay. So that's the sort of essential piece that does that translation.
Yeah, so what does this movie look like in the 1D case?
Oh, okay. So in the 1D case, so here's what the movie looks like. I've got the propagation Hamiltonian only applies to things with the red dot. That's where the action is, okay? So as this red dot goes from left to right, it triggers the execution of a gate, okay? And then when it gets to the end, it says, oh, I'm at the end. I need to copy everything over in order to process the next row of gates. So this little guy has a lot of work to do. It shuttles back and forth, copying all of this information over, and the process starts again. Right? Thanks. Any more questions?
For the 2D local Hamiltonian, when you're checking if the clock register is valid, wouldn't that take a lot of, like a Hamiltonian on a lot of qubits to check that you're in a valid clock register state?
As it turns out, you can do it with only local terms. So, and there are only so many local terms you have because there are only n squared local terms. So I can say, for example, in this picture, you know, the blue has to be to the left of the yellow. The yellow has to have a white one next to it. So I can use a small number of local terms to rule out exponential number of terms. Yes?
How is it going to phrase you the back and forth? So the red dot was reached to the end of this stage and it's going to, I'm not physicist, so I'm sorry.
Yeah. You don't need to be a physicist.
And then you have to copy all the states of the data from previously across the timeline as well. Does that mean that you have to basically remember all the individual states and the data associated with it?
Yeah, and those of us who have worked with Turing machines know how painful this is, but it's kind of a similar idea. So you've got this red state, and it has the capacity to remember a qubit. So you can encode a qubit into that state. So it coincides with this state. It absorbs whatever the value of the qubit is, and then it moves along to the left and plops that value here, and then copies it here. And then does the same thing for the next qubit. So it's this cursor, this little red dot that's moving around that sort of reads a qubit, encodes it, we encode it in its memory, and it moves that qubit over by n spaces. Yes?
This reminds me a great deal of the Minsky machines. Marvin Minsky loved this exercise.
Cellular automata kind of thing? Or yeah.
He also had a tape and was trying to find the smallest FSM that would allow him to do small computations, and he had to copy them over and over like this. And it turned into a game. And I was wondering if you might be able to utilize some of the same principles that he did, because much of this is classical logic.
Yes, yeah. So a lot of this is sort of a classical construction, and then we just happen to be copying qubits and right. So a lot of the sort of the mechanisms of the clock. So I don't know. Yes?
Did you say that you need the 12 dimensionalities to get the sort of information to pass over one another?
Yeah, and actually the dimensionality here is much higher. It's 12 now, and it was improved to 9. But yes, you need, because you're encoding, it's got to have control information from the colors as well as potentially encoding the qubits. So that's where the higher dimensionality comes from. So we don't know if this could be done with qubits, for example, in 1D.
But do you suspect that it's true, or?
I think I suspect not. I think you need some higher dimension to actually encode of all of this control in there. But in 2D, you can get away with qubits because you have the spatial. You can create sort of more sophisticated gadgets. Yes?
But somehow you say that for every two-dimensional Hamiltonian, there is a one-dimensional one corresponding to it, that somehow reaching the ground state is kind of analogous? Is that?
Yes. So I'm taking that 2D grid of computation and encoding it in a 1D. That doesn't mean that the physics of every 2D system can be translated into 1D. We're kind of talking about a very special class of propagation Hamiltonians for which this works. Okay, so one of the things that makes this particularly non-physical I mean, there are a lot of things here, but one of the particular things is that we need kind of a special Hamiltonian at each individual qubit of this construction. Okay, so it's highly non-translationally invariant. Whereas the typical types of systems that a physicist might look at have the interaction term between every pair is identical across. You decide on your one model, and that describes the physics between two neighboring qubits, and it's the same across. So you could ask, well, what is if I limit myself to translationally invariant qubits, what's the complexity there? So here's the problem statement. The Hamiltonian term itself is part of the definition of the problem. Okay, so that's not part of the input. That's fixed once and for all. The only input I give you is the size of your system. Okay, and then I ask you, if you take that Hamiltonian term and apply it to every neighboring pair of qubits in an n by n grid or a length n line, for example, what's the lowest energy of that system? Okay, so now the problem, by the way, has shrunk. The problem specification has shrunk in size. Usually in complexity, we speak of the running time as a function of the length of the input. So now, previously, my input was proportional to the size of the number of qubits in the system. Now it's exponentially smaller. I'm just telling you the size of the system. Okay, so it turns out that this is also computationally difficult, but we need a slightly different complexity class to describe it. This is QMA. I described for you before the witness sizes and the circuit family's polynomial in the number of qubits. And now I'm defining the same thing except exponential time. So this is an exponential size circuit. The witnesses are potentially exponentially long. Okay. The thing that's changed is not that the problem's gotten harder, just the input's gotten smaller. Okay. So we actually prove, in this case, that it's actually hard even in the translationally invariant case. And so just to appreciate what's happening here, we have an instance X. So we're doing this reduction. We're trying to show that this problem is hard. The only way of encoding the input in this case is translating it into the system size. Okay? So the Hamiltonian term is fixed once and for all. So any information about the language itself has to be encoded in the one Hamiltonian, finite size Hamiltonian term. And so in the reduction, we take an instance, X, we translate it into a system size, and we want this hardness to show. So we want this system or this Hamiltonian problem to represent whether X is in the language. So if there's a witness that causes X to accept, then the system has low energy, and otherwise it has high energy. So thinking now in terms of encoding these Hamiltonians as processes, the process that we're encoding now has a two-step. First, we count the number of particles in the system and write that number in binary on the tape, and then we execute and simulate the verifier on that input. So we first implement a binary counting Turing machine that just a little cursor shuttles back and forth and counts how many particles there are, and then encodes that count in a number that's sitting on the tape. And then we use that number as the input to the verification procedure. So somehow we're translating the size of the system into a string, and that string becomes the input to the problem that we're trying to solve. Okay? So the reduction is basically, we're executing this little binary counting Turing machine from one end of the, for n different steps, where n is the length of the system. And whatever it has sitting on that string at the end is the input to the system, and that's the reduction. Okay, so I've described it as a classical process, and the first step really is just a completely classical Turing machine, and we know that can be made quantum. So, and I should say that we moved from the circuit model to the quantum Turing machine model for a reason here. And the reason is that circuits are big. So to describe a circuit, it actually, in order to describe an entire circuit family, requires a lot of space. Whereas in order to describe a language using a Turing machine, I just tell you the rules of the Turing machine, and it's a finite object, which is exactly what we need, because we need to encode everything about that language in the Hamiltonian itself. Okay. So we need a clock that counts the number of particles in the chain twice and then executes. So I'm going to skip over some of the details here and talk a little bit more about what happens in the thermodynamic limit. So a lot of times what physicists are interested in, not the ground energy of an actual finite system, but what does it look like on an infinite grid? Okay, so in our paper, we actually show that if the Hamiltonian term is viewed as part of the input, you can actually show that estimating it to within some nth bit of precision is QMAX complete. But once you move to the infinite grid, you actually have the possibility of a much more powerful hardness result, which is undecidability. Okay? And that's what was done here in these two series of papers. I'm going to say a little bit about the 2D construction, but it was later improved to 1D. Okay, so they show that determining the spectral gap. So the input to the problem now is a Hamiltonian term. So I'm describing it using some number of bits. And I'm telling you, here's the size of the particles, and here's the interaction term described in a Hamiltonian matrix. And the name of the game is to know, if I were to apply that on the infinite grid, is that Hamiltonian gapless, or does it have a bounded spectral gap? And they proved that that's undecidable. Okay. So they actually reduced this to the energy density problem. So it really is, the construction really is about energy density. So they show that if you can compute the spectral gap, then you can compute the energy density. And then the hardness, the difficulty of the proof is really showing that the energy density, the density per particle, is hard to compute. So it's hard to determine if it's a constant or it approaches zero from below. Okay. So I'm short on time. I'm just going to say a little bit. I'm going to skip over the reduction part and just say a little bit about how the energy density works. So think of a reduction. I'm reducing sort of decidability, n. So n's my input, and I want to say, does the universal Turing machine halt if it's given n as the input? That's an undecidable problem, and I'm translating that into a Hamiltonian term. Okay? And if it halts, then I'm going to have an energy density that's bounded below by a constant. If it doesn't halt, then I'm going to have an energy density that tends towards zero. Okay. Underlying, so there's two levels to this. Underlying this is sort of a classical game of Wang Tiles, which is, I didn't put a date. Oh, I did, 61. So it's sort of an old problem where I'm giving you a set of tiles, and there are costs for putting certain colors next to each other, either above or below in the horizontal direction or the vertical direction. And I'm asking you to tile an n by n grid so as to minimize the cost. Sort of a classic sort of version of constraint satisfiability. And the construction makes use of a very beautiful tiling construction on the infinite grid that has, whose minimum cost tiling has this very beautiful aperiodic structure. And the aperiodic structure looks like this. Okay, so there are these exponentially sized squares. So each of these squares is of dimension 4 to the k. And the frequency of the squares varies inversely with the size. So in the infinite grid, I have lots of these little black squares and half as many of these blue squares and half as many red squares. And each of these squares is actually a little tile, little square of tiles. So this was known before, And they use this as sort of the substrate to their construction. So a tile itself, a particle in this construction itself has two components. It tells you what the tile is underneath, and then there's some sort of computational process happening on top. So here's the picture. Here's the tiling, and sitting on top of it is some computational process that we're kind of simulating on the boundary of these squares, okay? So the Hamiltonian encodes the input. We use the process that's taking place on this 1D line is we're going to translate that n and write it in binary. And then we're going to simulate the universal Turing machine on that input for some number of steps. Okay? If we halt, there's a cost. If we don't halt, there's no cost. Okay? So basically, if the universal Turing machine never halts, there's no costs on any of these squares. But if it does eventually halt at some finite 4 to the k, it runs for a certain number of steps, 4 to the k. If it does eventually halt, then all of those squares from 4 to the k on up will have a cost associated with it. And that will result in a constant cost over the infinite grid. So if it eventually halts, then there's a constant cost. And if not, then it's 0. So that's how we get the differentiation. So here's sort of in a nutshell, if the universal Turing machine halts in some finite amount of time, then the energy is bounded below by some value because the squares of that size on up incur some cost. And if it doesn't halt, then it's 0. So a few things about directions. We still don't know how to actually characterize the complexity of computing translationally invariant Hamiltonians in the thermodynamic limit. So this result tells me it's undecidable to tell if it's 0 or some constant. But what if I wanted to compute that constant? Is there a way to characterize the complexity of that problem? I'm not even sure how to characterize it as a complexity problem, because for a given Hamiltonian, it's just a number. So we need some sort of even framework to even get it in the framework of computational complexity. But we still don't know and that's really kind of, at the end of the day, what many physicists are doing when they're actually doing these simulations. This is what they want to actually estimate is this energy density. The next thing is that these constructions, they're obviously very intricate and probably not particularly stable. So if I have some measure on Hamiltonian terms, if I tweak it a little bit, if I go epsilon away in this space, is it still hard? Is a hard instance surrounded by easy instances? We don't know much about that. So I think there are some interesting directions to go with respect to stability. Obviously, these are highly intricate constructions that don't really necessarily represent the physics seen in nature. So you could definitely ask, what about the common models that are studied in physics? Okay, so I'm going to go quickly over a few things in order to get to some questions at the end. So one question that we studied is the Bose-Hubbard model, which I have particles sort of hopping through the system. And Childs, Gossett, and Webb look at this very classically studied natural interaction on an arbitrary interaction graph. So we're kind of going in the other direction. I have a very simple interaction term, but now the input to the problem is a graph. And I ask, what's the ground state of this Hamiltonian if I apply this interaction term to every edge in a graph? And it's actually, in the realm that they're looking at, it's actually equivalent to an XY model, another commonly studied problem. And it turns out that this problem is QMA hard as well. So this was later improved. Their original construction had self-loops in the graph, which is highly non-physical. So there was a later improvement with a construction that didn't have these self-loops, which actually corresponds nicely to the XY model. So the improvement kind of got rid of those self-loops, which is a little bit more natural. But the interaction graph is very complex, okay, because it's encoding these kind of computational gadgets in it. They mention new directions and sort of playing with the Hamiltonian terms. For me, the more interesting direction is how can you simplify the graph? Can you get a hardness result if your graph is planar? What if you have a grid and you just have some subset of edges on the grid? Is that hard? Is there a point at which this problem becomes easy? Okay? At the end of the day, physicists are just looking at this on an n by n grid. And I don't even know how to frame that as a computational problem, because that's just a number again. Okay, so you probably just converge to some particular number as n grows. So I'm not sure that there's a reasonable way to formulate this as a computational problem, but we don't have a place where it actually gets easy. Okay? I don't have time to cover this, but another family of results looks at the opposite problem. So I'm giving you qubit terms, and you can have an arbitrary interaction graph, and any scaling of those terms on the edges. So I give you some set of finite terms, and there's an analogous work to this in the classical realm, where I give you some type of set of terms, and I ask you if you can apply scalings of these terms on the edge of the graph, what's the complexity of that problem? And it turns out you can actually completely characterize the complexity of these terms into these different classes. So at some point they're P, NP complete, stochastic, MA complete, and QMA complete. Okay? What's unphysical about this model is that you can have negative and positive coefficients, which is typically you only have positive coefficients or negative coefficients, arbitrary interaction graph, and then these large coefficients, because we're encoding a computational problem in this interaction graph. So, and that was later improved in a subsequent paper where they look at, let's say that you just have positive coefficients on this, and again, the space of 2 qubit terms is sort of completely characterized in terms of their complexity. And then they also look at 2D and the 2D grid and the 2D triangular grid and get QMA completeness results there. The most interesting direction, I think, is to grapple with this idea that the coefficients themselves can be quite large. So can you do this with smaller coefficients? I kind of want to end with this this picture, though. So these are the 4 classes that they can categorize the complexity in. What seems to be missing from this picture, and it's curious to me, that BQP is not here. Okay? And in all of the variations of local Hamiltonian, and there are a gazillion, I haven't even talked about commuting case or other cases, I don't know of a single instance or variety of the problem that we can show is provably in BQP and not known to be in P. So you could concoct one artificially. If you think back to my adiabatic picture, I could imagine the class of local Hamiltonians that are the ground states of these propagation Hamiltonians where you have an input and no witness. That's going to be BQP complete, but that's not a terribly natural version of the problem. I'm thinking in terms, and I wouldn't know how to encode into the local Hamiltonian terms that you don't have a witness. So what I'm thinking of is a local Hamiltonian term. You tell me what the dimension of the particles is. You tell me the types of interactions you can have between these particles. You define how they can vary from edge to edge. Is it translation invariant? Is it not? There's another thing to vary. The interaction graph. Is it a grid? Is it an arbitrary graph? I don't know of a single way to sort of define a problem that we know a quantum computer can solve it, where we don't know that a classical computer can solve it. And I would think that quantum computers should be useful. I mean, we expect that quantum computers will be useful in solving ground states. I mean, I talked about this morning. They're in the process of working on this. In much the same way, classical computers are very useful a lot of the time in solving NP-hard problems. But in the classical world, we have this situation all the time where you have some NP-hard problem, and you add a bunch of constraints on it, and all of a sudden it falls into P. But somehow in this picture, we start with the QMA complete problem. We start adding constraints to the point where you can no longer encode Boolean satisfiability, and it falls into P instead of BQP. So that's a little curious to me. And it would be interesting to know, are there sort of provable cases where quantum computers are actually useful in solving these local Hamiltonian problems? I'm not aware. Now that I say it in front of a room of 100 people, maybe 5 people will raise their hand and tell me a counterexample, but I'm not aware of an instance in which that's the case. So that's sort of interesting. It's interesting to me, is there a way to limit these so we can actually get a quantum algorithm for them? And maybe it's the lack of algorithmic techniques. Maybe quantum computers aren't designed for this particular type of optimization problem. I don't know the answer. So I'll end with that conundrum.
Questions?
Have you thought of how to simulate open quantum systems?
Open as in, so it's connected to some bath or something?
Or directly using semi-group operators, Booleans?
And there we're looking for Gibbs states because they're mixing with the bath. So yeah. I mean, there is a whole literature on computing Gibbs states, which I think would probably speak to that more directly.
And there's a whole literature in the classical world of sampling probability distributions.
Yes.
But there doesn't seem to be an analog in the quantum set of workers who do the analogous thing for the quantum in your world of local Hamiltonian.
Yeah, so there's this beautiful quantum metropolis algorithm. I'm not aware of much in the way that proves convergence bounds for that, or for example.
Complexity classes.
Yeah. So, yeah, I don't know. Yes?
If we take an Hamiltonian whose ground state encodes a factoring problem, wouldn't that be an example of the case for which...
Yeah, and just like I said, you could imagine even a more generic case where you have the class of Hamiltonians that just models, whose ground state models the evolution of a circuit. Certainly that's BQP complete. I don't know how to describe that class in sort of this local Hamiltonian framework. I mean, I wouldn't know how to say you've got these local Hamiltonian terms, but somehow you've got this construction that doesn't, when I define the local Hamiltonian problem, it doesn't say anything about inputs or propagation or witnesses or anything. So you need some way to define your class that disallows for this open witness in there that makes it hard. And I don't know of a natural way to sort of define that in sort of these local Hamiltonian terms. So you could certainly manufacture a problem whose ground state is hard, but it doesn't necessarily naturally fit into this, I give you this set of terms and this set of types of interaction. So.
Would it be so hard to imagine that within these rules that you've set for, if you disallow that in fact as soon as you, as soon as you escape NP, you actually do anything.
Dive into P. Yeah, and I wonder if there's sort of a general way of framing that problem. So, yeah.
I mean, these dichotomy theorems, right? They have this sort of
flavor to them.
Once you allow sufficiently many things, then that's where
you end up. So yeah, I don't know exactly. I mean, you have to sort of define the parameters of your local Hamiltonian problem appropriately in order to get that. But I feel like there's some phenomenon like that happening here.
Yeah, it's really interesting.
Yeah.
So we're now breaking for